we're going to explore a method that enables us to represent OREDA data with the inclusion of shape parameter typical of the Weibull distribution. So this first method is for the inclusion of the Weibull shape parameter. An alternative method we're looking is to the inclusion of the log normal standard deviation. So what we've done, we have some asset here, and we've got a centrifugal pump, a motor and a heat exchanger, and we've also collected some failure modes / failure mechanisms, say for example for the bearing. We have investigated the range of the beta in terms of the lower value of beta and the upper value of the shape parameter, and the information we collected indicates we have a variation between 3 and 5. The same thing matches for the seals. We have a variation of 3 and 5. While instead other failure modes, like for example cavitation or sudden overloads, have a behavior that resemble the exponential distribution or random failure. So we collected these data, and the idea is if we were to take some OREDA data in terms of mean life, how could we include these? But in particular, how could we change the scale parameter of the Weibull distribution so that the mean life is exactly the one stated by the OREDA, but at the same time we also include the shape parameter. So what we've done, moving on here on the right, we have the formula for the mean life of the Weibull distribution. The mean life is the eta multiplied by the gamma function of 1 plus 1 over beta. And what we've done, we constructed a table with a range of beta that is well within these values. So we started off from infant mortality all the way up to a value of 5. And then in this part we basically just compute the gamma function of 1 plus 1 over beta, and the eta function is derived by the simply the mean life divided by the gamma function of 1 plus 1 over beta. And we know that the gamma function of 2, which is the result of 1 plus 1 over 1, is equal to 1, and therefore with the beta equal to 1, we have that the mean life is equal to the eta function. So the scale parameter matches exactly the mean life, and that's exactly what happened on the exponential function, which is just one scale parameter without the shape parameter. But for all the other values, the results are going to be different. Okay. So we computed this value, and now we want to see what the difference is. We want to see what the difference is between the eta and the mean life. And in some cases will be negative, in some cases will be positive. And then we plot this value. We plot this delta, which is the orange line, which is exactly this information. And then we're trying to fit that variation with the model, and we try a variable model, and we stuck to the exponential, and this is the actual exponential model that we fit. And by doing that, we have a model that enables us to then change perhaps the value of our mean life, and we have a tiny little variation here that we'll not even be able to see then, but essentially these delta remain pretty much the same. And so the exponential fit, we're not going to change the exponential fit, but we think is an adequate fit for the purpose. And to verify this, we for example take the value of one of these beta, say for example 3.6, which here generated an eta value of 38,841. And what we do, we fit the exponential model, which is this exponential model that we found, and it tells us that the delta, so the extra bit that the variation between the eta and the mean life is 0.115 roughly. Okay, so therefore we take we take the new eta that we estimate from our model is basically 35,000 plus 1.115. So the result is we have an eta of 39,000 against an eta of 38,831. And we want to see what the difference is in terms of results, in terms of mean life. So if this one gives us 35,000, what value will it give us with the model, essentially? Because effectively we want to take this model, being able to apply to any value without having to worry about it. So to do that, we have to switch to Weibull++. So we go to Weibull++, we create a blank folio, and we don't put in any data, but we just click calculate. And we want to put in the parameter of the model. So it's 3.6 for the shape parameter and 39.24 for the scale parameter. And then we click OK. So we fitted this model, and now we want to find the mean life. So we go to the mean life, calculate, and we have 35,164 against the, say, 35,000 from the OREDA. So we feel that with this approach, it could be a simple way of incorporating the OREDA data into a model that takes into account possible wear out. Thanks very much.